be made available. Any questions we've received, I'll create answers to those questions, and it'll also be sent out to anybody that's joined us. At the moment, we've got quite a lot of people. We've got people from Australia, from Malaysia, from Canada, South Korea, and also from Europe. So welcome everybody. I appreciate everybody joining us, and without further ado, we will start. So the whole objective of today's webinar is really to identify whether or what valuable data can be collected using machine vision technologies for ITS. And in moving forward on that, what we'll do is we'll start with, sorry, slight technical issue immediately. We'll start with a proposed agenda. Before we start, I'm going to really go through what is ITS. There's been a lot of discussion as to what it really means or what it really stands for, and I'll hit that. I'll then go through what the past, present, and future is, particularly looking at the future as opposed to dwelling on the past, and then really try and identify what's different about machine vision and the ITS environment. I think it's important to actually go through that just so we really understand what we need to do to move into that particular vertical. Our landscape of the future, what we're really expecting and where we're expecting visioning technologies to really play a part, and then really looking at what data is available from a camera and how that can be used, and then answering that all important question. So before we go any further, what is ITS? And the reason I put this up is because I get everything when I go around and give these presentations to integrated transit solutions to actually intelligent transportation solutions. And let's just be a bit clear here. The whole importance of intelligence is that you're using data in a way which is actually going to give you some real value. And then transportation is basically anything which moves. And then solutions, if it was systems, it would really relate more to the processes or the electronics behind it. Solution actually relates to the entire package. So it's intelligent transportation solutions. So what is that from a traffic point of view? Let's have a look at traffic, then transit, then a couple of other bits and pieces. I'm not going to go through all of these. As I said, I won't be reading the slides. But the kinds of things that we know and love are like the speed enforcement, the red light enforcement. But actually some of the more important things that are coming to the market now are things like the wrong way running, the lane obstruction detection, shall we say more the safety critical elements which are playing a really big part in ITS right now. And then I really want to concentrate a little bit on the longer term markets, things like the integrated corridor management. I'll just give you a quick overview of what that is, and you'll see that on the next two slides as well. But integrated corridor management is effectively identifying a small location, a small area, it could be a corridor, it could be a small town even, and really managing the transportation environment completely within that area. It's as a holistic view. So it's really looking at things like, okay, looking at how, or the correlation between traffic and transit, between transit and walking, cycling routes between modes as an example. And it's really trying to identify what you need to make it more successful. So as an example, if we had a ball game going on, then we may want to put additional transit services on to help people get in and out of the environment. That's something which is playing a really big part now in North America and Europe for that matter, and is starting to make an appearance everywhere else as well. And it's something which I personally believe will actually make a big difference as we move forward in really managing traffic and transportation in general. The other thing I want to just hit briefly is the connected vehicle. Connected vehicle has been on the books now for around 10 years. It's changed its name 5 or 6 times. But the idea behind it is to get vehicles to communicate with other vehicles as well as to communicate with the infrastructure around them. And the idea behind this is using vehicle-to-vehicle communication. You can create a wireless mesh network. From vehicle to infrastructure, you can also do the same. And the idea behind that is as you move forward with this, you can actually start identifying when vehicles are braking or when there's weather conditions which are making people turn lights on, headlights on, or windscreen wipers. and start communicating that back. So, for instance, if somebody's braking hard up ahead of you, you can start putting speed restrictions in to try and slow traffic down before they get to that point. And it actually will play a really big part as we move forward. But in reality, because it's only starting at this point in time to be installed in vehicles, it's really going to be about 10 years away. Transit, again, I'm not going to go through all these slides, but the things that we'd probably like to see within a transit environment from a camera perspective are things like passenger counters, particularly now that you've got facial recognition and the facial recognition algorithms as such. Instead of having, shall we say, mechanical passenger counters which are based upon the average weight of a person, you can now actually do it on a real identification of all the passengers in there. Other kinds of things that we would like to see as signals past the danger, that could be managed by cameras now. Stop management could clearly be managed by cameras, automatic vehicle detection, and so on and so forth. This next slide is what I'm classing as the other stuff, because it's probably some of the most interesting stuff as well, but things like the autonomous vehicles and the driverless vehicles that are being developed by the likes of Google, Carnegie Mellon University, and I believe there's several other organizations delivering these or developing these at the moment. Drone technology is also a big part, and some people may argue whether drone technology is ITS, but in reality, you know, at this moment in time, that's certainly because it's transportation, it's moving, therefore it's classed as in the transportation, in the ITS field at this moment in time. So looking at ITS, the past, present and future. Sorry, before I go any further, any questions so far? No?
No questions at this point.
Perfect. ITS, the past, present and future. What you're really looking at is, if you know, as we move forward, there hasn't been a lot of intelligence, as I said earlier on, in ITS. When we started in the 1990s about this, it was really about data collection. There wasn't really a lot of emphasis put on the reporting elements, and really all you got out of it were basic reports, you know, counting reports, you know, how many cars on the road at any given time, day or night, and so on and so forth. The 2000s became more of an integrated environment, and ETL stands for extract, transform, and load. And the idea behind that was, how do we get data from one system into another system to give it a semi-seamless environment? And that worked very well, and certainly, you know, because ITS has been built with many proprietary systems, that's actually become the only way of really doing this. In 2010s, though, the big buzzword has been big data. But I'm going to change that, because big data without data visualization really doesn't give you a great deal of benefit. It's really the visualizing of that data which really helps you. And I'll show you, I'll demonstrate that in a few minutes with a couple of slides forward. Then you start looking at modeling concepts. They've also changed quite dramatically over the last 20 or 30 years. It started with macroscopic, and basically macroscopic was taking a little bit of data you could really get your hands around and really identifying what that data could do, and then putting some real assumptions in with that data. And in reality, you're getting a modeling tool which is about 20% accurate, 20, maybe 30% if we're really lucky. The whole other end of that spectrum is a microscopic, and the idea of microscopic is to really identify every vehicle on the road and every vehicle's turning movements on that road at any given time. So mesoscopic is somewhere in between, and mesoscopic is where we are currently. And we cannot do microscopic at the moment, to be very clear about that. But mesoscopic basically gives us about a 50% chance of really understanding what's happening on the road. It's great when the road is running as it normally would. It's not particularly good when there's something untoward happened on that road. A ball game would be an example, Thanksgiving would be another example, or an accident, construction would be others. Now the ball game is probably not the best example on the basis that you can actually start to plan that because you know what's really happening. And then the ITS requirements have also changed over that time. It really started with historic. In the 2000s I was heavily involved in real time, but it became very apparent with real time that real time was really looking at a subsection of historic. There's always latency involved in real time, and therefore it was always slightly old. It may not have been very old, but it was slightly old. But really the holy grail was predictive. And what we're looking at now with the big data philosophies and microscopic model is a way of getting to that predictive environment that we absolutely need to really manage our roads as well as we need to. And then the modeling element has changed as well. The process modeling, it's gone from data, which was purely data in the 1990s. It really didn't give you a great deal of benefit. The 2000s were about information, and the 2010s, I'm absolutely confident, will be about intelligence. But that intelligence will only happen once we have big data, microscopic, and a predictive environment. Any questions?
We have one here. So why do you believe that prediction is so important?
Oh, that's a good question. Basically, what I'm looking at is to really manage the road environment, we really need to understand what the knock-on effects of an incident is going to be. And the only way we're going to do that is really understanding in a microscopic model what the predictive elements are going to be as well. So prediction will be able to not only tell us what's going to happen in a normal environment, but also what's going to happen in the unusual environment, i.e. in the case of a major accident. As an example, when I was living in California, a truck laden with fuel hit a bridge. It spilled the fuel ignited. The driver escaped quite miraculously, but the entire bridge melted and it fell down. In that situation, without a microscopic model, you had no way of predicting what was really going to happen. With a microscopic model, with prediction, you can really understand where all those people are going to go who would otherwise use that road at any given time. And that's why the predictive and microscopic and big data and intelligence layer really, really matters. Oh, you have another question, sorry.
One more question here that popped up is how can this proposed approach be realized?
That's a difficult one to answer, and I may have to come back to that towards the end. But the idea behind this is most of this is already being realized. Everything in the 2000s has already been realized, and the 2010s is really already happening. There are already predictive models on the market which are not yet 100% accurate. They're probably nearing about 80% accurate. The microscopic model with the OD modeling is probably the most important element of this. OD is origin destination. And the idea behind this is once you get to the microscopic model, you can really understand where everybody's come from and is going to, and therefore what their turning movement is going to be. Once you've got that, you can realize this model. Any other questions, Francis? Sorry, I should have asked that.
No more.
So before we go any further on this, I really want to go through what the current sensor capabilities are and what the current limitations are on the ITS environment or within the ITS environment. I'm going to go through this pretty quickly. I'm going to dwell on a couple of these on the next slides as we move forward. But the first one, and probably the most prevalent one, no, not probably, the most prevalent sensor are loops. And they're the big round circular blobs you see on the road surface, generally with black tar outlining a ring. It can either be a ring, it can be a square, it can be an octagon, it can be a rectangle, but basically underneath there is either one or two coils of cable. It's very simple. And basic physics are every time you have a metallic object passing a loop, you get a slight induction. What that tells us is effectively there is a presence of a vehicle or not. It's really a flip-flop. Now there are people that will argue that that can actually tell you which vehicle it is and what have you, and it can, but it's never used in that way, and not in the real world environment. So right now they're just flip-flops, yes or no, or 1 and 0. And what that tells you is effectively that there's a vehicle present or not. And what they do is put these in series so that with a certain distance apart, so then you can know that the time it takes to get from one loop to the next loop, that time, based on the distance, you can identify the speed. The problem is that if only 60%, or actually in some places a lot less than that, are working at any one time, that means the probability of actually being able to get two loops in close proximity which are both working is actually quite low. And there are millions of these in existence. But the problem is because they are so non-robust and actually reasonably expensive to install because you have to close down a lane every time you reinstall one, you are now in a situation where some places have actually refused to use the data that's being provided by them. Then enters magnetic pucks, and they do exactly the same as a loop. In fact, there's a small picture of it there. They're about 3 inches across. They have a battery life of about 7 years. And the idea is they do exactly the same as a loop. You bury them on the road, you forget about them for 7 years, and they give you data for 7 years. Unfortunately, again, they have not been seen to be as reliable as they should be. And again, that gives you a problem. Radars have been around for years. They have a real issue with maintenance, really. Basically what happens on radars is that over the course of time, and in fact, they should be recalibrated every month if they're set up correctly. And the other problem with them is obviously you have shielding, so they're generally set up on the side of the road, they sideswipe across all lanes. If you have a big truck, it can actually shield several cars behind its shadow, which means it's not particularly accurate. Now, all those first three do not identify the specific vehicle. Now, to be clear, my philosophy, and after working with the Departments of Transport and transportation agencies around the world, it's absolutely essential within a microscopic model anyway to identify every vehicle on the road. And if you can't identify the vehicle, you can't do that. That said, I was in a FLIR webinar a few days ago, which actually suggested that transportation agents don't want to do that. Let me be very clear. In most countries, and very few countries are against this, but in most countries they do want to identify every vehicle, not only because of ITS, but also because of security issues as well. So by using a camera, you can actually do both in one go. Toll tag readers are very prevalent. Unfortunately, not all roads are toll roads, and when you haven't got toll roads, you can't have any reading, so in reality you get about 10% coverage at best, and that's only in very urban environments, or very, shall we say, populated environments, I should say. Bluetooth sniffing was actually developed by the University of Maryland, and the idea behind that is using your cell IMAC address to identify which vehicles are on the road at any one point. Unfortunately, the penetration is pretty low, and you have some real issues with, as an example, I'll give you a real-world example. You have a busload of kids going down the road. You've got 50 kids in a bus, all with a cell phone. It's giving you the answer that actually there's 50 cars going down the road, and it isn't. And again, so you have to start taking out all these outliers, and it gives you a very narrow band of information you can really use. GPS floating vehicle data and cellular floating vehicle data, I will go through in the next two slides. So, but they're very good technologies, pretty expensive technologies, has to be said, to get operational. But there are accuracies with those, but I'll hit those on the next two slides, as I said. And then you've got cameras at the end of all of this, and cameras will provide. Now, going back to basics a little bit here. ITS requires three basic variables: speed, occupancy, and volume. And to be clear, occupancy means how long a vehicle exists in the sensor line of fire. Okay, so for instance, if it's on a loop, it'll be on a loop for a third of a second. And volume is the number of vehicles on the road in any given stretch of road or any given distance of road. Now, there's one other thing which is now becoming much more important because of some of the tolling things, is classification. And that's the type of vehicle it is. And there are, I think now there are 8 different classes of vehicle, but there's no technology, to my knowledge, who can actually identify all 8 of them. And I believe you can do all of that with a camera. But the camera is pretty much the only technology that can identify not only every vehicle, but identify the speed, volume, occupancy, and classification from a single device. Before I move on to going in through GPS floating vehicle data and cellular floating vehicle data, any questions?
Sure. There's one that did come up, and it is virtually everyone uses loops. but how can they be so non-robust?
That's a really good question. Let's be very clear. Loops are just literally a piece of wire, and they're about, for want of a better, 10 millimeters across, probably not even quite that large, 8 millimeters across, diameter, sorry, I should say. And basically they're just two loops in a road. They're buried anything from ½ an inch to 3 inches below the road surface. And the problem you've got is every time you want to resurface the road, guess what you do? You take off the top layer. That takes off the loop. If you have an overzealous snowplow driver, they'll go down the road and they'll scrape off the top layer of your tarmac as well. And they are simply not robust. There is, the other third part is you're grinding a circle, let's say a circle, it could be a square, it could be anything as I just said, but into the road surface. You're then putting a piece of fairly brittle wire into that environment. Now that's got lots of abrasives in there because you just ground it. It's a very non-robust technology, unfortunately. Very useful, but not very robust. Any other questions before I move on?
That's it for now.
Thank you. Okay, forgive my poor graphics. What I've got here is effectively 2 loops or 4 loops on a road. As you move up, what you can see happens, the car moves forward, it goes over the first loop, it transmits to a roadside device that then transmits to a back-end office. As it goes past the second one, it does the same thing again. And that's really how loops work. Now clearly, if only one of those loops is working, all it can tell you is the presence of a vehicle. If both are working, it can also tell you speed. So the fact of the matter is really binary delivery. It does tell you occupancy. Occupancy, remember, is how long it's been on that sensor for. It does tell you volume, how many cars are passing it. And from that, it can deduce, to a certain extent, the flow of vehicles on the road. It counts every vehicle, which is actually very, very good. It can give you speed if you put two together, but as I said, it's really not robust enough. It's not robust enough for today's technology requirements, I'll put it that way. GFVD. Now, this is real data. This is data I've managed to collect. And basically what you get is points in time. And as it builds up, you can see that it gets more and more and more points. And this is for a stretch of about 3.5 miles. Sorry for everybody who still works in kilometers or is working in kilometers. We still work in miles. And it's over a given course of time between 11:20 a.m. to 1 p.m. But as you can see there, you can see something's happening on the right-hand side, but you can't really say what. Well, let's look at this in a little bit more detail. Let's look at it now, looking at the data visualization, the big data philosophies we spoke about, and start putting some line traces on here. And what we can see here is now we can actually start seeing which vehicles are which. We can see that some of the data has been lost halfway through, and that's fine, we expect that. But again, even now, although we can see every vehicle on the road, well actually, let me rephrase, we can see about 4% of the vehicles on the road, that's all this will give us. And we still see there's something going on over here. We can really, until we start putting more data visualization tools in place, we really can't see what's happening. Now that we've got some color on here, we can see that the yellow effectively stands for slow down, the red stands for stop start, and the blue is, the black, clearly colorblind this evening, is effectively full stop. Now clearly full stop means you're going forward at a slow pace. What you can see here, is that over the course of about an hour and 10 minutes, in fact, congestion has started off in the bottom right-hand corner, down here somewhere. In fact, I'll get the next part of the slide. Started on the bottom right-hand corner, and you can see predictably where it's going to go to, assuming the flow of traffic remains constant. Unfortunately, it doesn't remain constant. So in peak hours, you have a much higher flow than in non-peak hours. But assuming the top remains constant, the flow remains constant, then what you'd get is every hour and 10 minutes, you get 2 miles of additional congestion. So it does give you some element of prediction, assuming constant flow. And that's really the crux of this. So looking at this, yeah, we've got some rich data availability, and as you can see, but it's still only about 4%, to be clear. And let me be clear where they get this data from and why there's another element of shall we say, element of incorrectness, for want of a better way of phrasing it. This data comes from the likes of the FedEx vans, which have automatic vehicle location in them, the UPSs, taxi drivers, buses. And none of those vehicles go at constant flow. A lot of those are stop-start vehicles. So it doesn't give you a true representation of what's really happening on the road in most cases. But yes, you can correct some of that through algorithms, and that is corrected through algorithms, but it still gives us another layer of latency which we would otherwise do without. Looking at cellular vehicle data, and saying this is actually true data as well, and what you can see here is all the points which are collected from cellular vehicle, from the cell towers. And what happens here is every time you go down a road and you're on a cell phone, the cell phone is constantly checking to see which antenna is closest to it. Now, because we use our cell phones far more than they were ever envisaged to be used, and we use data far more than was ever thought was going to be used as well, what actually happens is you have towers with multiple cells on them. And it'll constantly be swapping between those cells, which doesn't help us a lot. Looking at this in a bit more detail, you can put some lines on here to really draw some standard deviation on this. What you can see, though, is right in the middle of this, at 2.5 miles, you start getting more cell communication. And that's probably because you've got to slow down. People are on the phone saying, oh, hold on a minute, I'm going to be late. But right where it really matters at mile marker 3, you've got no data at all. From mile marker 3 to mile marker 3.25, essentially, you have no data. And that's because it's stopped. And stopped means that it's not, although you're still on the phone, the signal is not being transferred from one cell tower to another. So right where you actually need the most data, you're getting none at all, and it's effectively the same as saying there is no data coming in. Now you can get around that again with algorithms, but the biggest issue, I suppose, with cellular floating vehicle data is not so much you've got this volcano effect, is what it's called, but actually the biggest issue is that because you're talking about a cell tower which is effectively a kilometer in diameter, if you have roads beside roads, such as in America we have frontage roads beside freeways, you can't tell the difference. You can't use this in an urban environment, because in an urban environment where you've got city blocks, you could actually be covering 5 or 6 different roads, and it doesn't know the difference between any of them. To the cell towers, it's essentially the same place, and that gives us a real issue as we move forward. Then coming on to some camera technology, what we've got here, and forgive the poor picture quality of this, but as every vehicle's going past, basically what happens is it reads every vehicle, and it can be one camera looking at multiple lanes, or it can be multiple cameras looking at a lane each. Reads each of those. In North America, it would also have to identify the state. In Europe, it would have to identify the country. Bear in mind that many of the European countries are quite small, and you get quite a lot of transients between those countries. But the idea behind this and the benefit of this technology is that you can actually read every vehicle on the road every time. And the few percentage that aren't read, there are, and at the moment, that's only about 2 to 3%. They can be brought back to a back-end system and then be interrogated through data visualization tools and the human eye to identify what's going on. It has huge advantages. The ANPR or ALPR, automatic license plate or automatic number plate recognition, has one huge advantage. It's about 10 times better than a naked eye. So what a naked eye cannot see, generally speaking, the camera can pick out, particularly with some of the newer technologies. So it's very good. Before I move on, any questions?
Sure, yes, there is one question. It's how can a camera see a license plate when the image is so unclear?
Yes, it's quite interesting actually. And this comes back to the point I said before, the fact of the matter is ANPR recognition is now as high as 99.2% in some areas. That's huge. I mean, at some, looking even 2 years ago, we were lucky to meet the 90% in some places. The fact of the matter is it's got better and better. So the best I've seen now is it can read accurately a license plate at 8 pixels. That can go up to as high as 12 to 16 and much bigger, of course. Obviously, the better the camera, the more megapixels on the camera, the better it is to see the vehicle as well from even a further distance, and the better opportunity to capture that is. I was slightly involved in the London congestion charging, and even back then we were able to, and this is years ago if you remember, even back then we were able to read license plates from quite some distance very, very accurately. So does that answer the question?
Yep, it does.
Excellent. Any others, or shall I move on?
You can move on. There is none at this moment.
So I think where we're at the moment is we believe it can really do it, but we really need to also understand why it's different. And it really is different. Machine vision is, and the machine vision requirements are very different from a normal machine vision application to ITS. And the first real difference is the fact that it really has to be an IP platform. Now these are essentially plug and play. Departments of Transport and transportation agencies, they put them up on a gantry, they plug them in, they calibrate them, and then they forget about them. Other big major difference is that you have to have compression. And depending where you are in the world, depends on whether you'll have H.264, MPEG-4, or Motion JPEG. And even now that's changing because we're now looking at H.265, which has even better compression ratios. One of the other areas which is absolutely different to a machine vision environment is what you have to do with that image. Machine vision generally wants a completely raw data image, whereas ITS really wants pixel correction, color correction, still image stabilization, and any number of other firmware/software requirements. Again, from an operating system point of view, we're looking at either Linux or Windows. Again, that depends on the geography. And then the sensor requirements. Again, these change depending on what you're trying to use it for, but I would say that probably the most important is high dynamic range. I would say a fast shutter, although if you have a lighting array, that have to change. I'd be triggered with the lighting array in mind. I think you can't get away with less than 30 frames per second, although some do, but I wouldn't. A low lux and then megapixels. The more megapixels you have, the more lanes you can cover. If you want to cover more than one lane, if not, then again that remains to have some discussion about. Communications will change as well. Most of them, certainly in North America, it goes back to a fiber network. But even then, despite that, there are still situations where you have to connect to GSM network, CDMA network, or any other number of communication channels that are out there. But probably the most important is the temperature range. I've got here -40 to +65, which is the normal standard operating temperature range of ITS. I challenge that, and I don't believe it's enough. +65 is ambient temperature. I think the world's greatest temperature at the moment has ever reached is 53.5 in Death Valley, so not a problem with that. But -40, we constantly go below -40 in all sorts of geographies, including North America. Russia would be another classic example of that. Saudi, probably not so much. Australia, I doubt it, but I could be wrong about that one. But the fact of the matter is you can extend the -40 by having internal heaters in your enclosure, so that, again, you can get past that quite easily. Oh, sorry, we have a question. I apologize.
Yes, we actually have 3.
Oh.
So the first question is, how many megapixels are required?
At this point in time, Francis, I'm going to say I hate you. It depends on who you ask. Personally, I don't think you should do away with, it depends on, it really does depend on who you ask. At the moment, probably the most prevalent ITS sensor requirement is called SIF, which if I remember rightly is quarter VGA. But that will never be able to do automatic license plate recognition. It just isn't capable of doing that unless you have a very front-on view. Thereafter, it's probably VGA. But in reality, if you're really going to do license plate recognition, I think you need HD as a minimum. If it were me, I would go for 2 megapixels on per lane, but then you could extend that in all sorts of ways. Because in reality, you don't really want a square picture on ITS. You really want an extended picture or extended set of pixels. So from my point of view, it really does depend on what your application is. I wouldn't go below HD for NPR. So next question, sir.
Sure. So the second question is asking, is HDR important?
Yes, I think it's one of the most important things. I have met people that say it's not at all important because if you trigger an IR lighting array, it really doesn't need it. Again, I'll challenge that because in most cases, the IR array can only see, say, 20 to 24 meters. In reality, the camera can see a lot further than that. So with a high dynamic range, you can see you get a better focal distance. That said, if you're using it within a tolling environment set to 20 to 24 meters, then probably not. What I would say, though, is that by putting high dynamic range in there, you're not detracting anything. It's probably not costing you any more based on the sensor type, but also you're able to use it for a lot more applications than you otherwise would be able to. You said you had 3, sir.
Yep, and we have one more. And this third question is asking, is an IP platform the best approach?
Well, I think, yeah, I think to be blunt, it's the only approach for ITS. It's a good question, and it does bear some extra thought. At the moment, everyone I've ever worked with in ITS has always used IP, and the reason for that is because they're linked to a back-end ATMS system, which stands for Advanced Traffic Management System. And the idea behind that is they basically collect images, and they will only collect them through a web environment. Can it be set up another way? Probably, but it would cost more, it would take longer, and it's not the way the transportation departments currently work. So yeah, I think it's the only way at this point in time. So in summary, it's a very different market. It requires different hardware, different software, and there are completely different applications that run on it. And I think, based on that, it's so different that it does need a different philosophical approach to how we develop a camera for that. So let's have a quick look at the future here. Let's identify where we're going and why we're going there. I'll bring up a graph, and I'm going to apologize up front that the data only goes up to 2009. It simply hasn't been available to get accurate data in the same format as I received this in any later than that. But this tells us a story which I really need to go through. If you look at each one of these ribbon lines, it basically shows you a year. And what we're at the moment is it starts off at 2005, I think it is, and goes on to 2009. 2006 is the yellow one, and that's the one I really want to concentrate on at the moment. And that's where we had peak conditions. And if you start looking at that, what happened is throughout the day and night, you had more traffic on the road than you've ever had before. And because of that, people were leaving on their journeys earlier and coming later. Now in 2006, after 2006, sorry, we had an economic downturn, and that had a real impact in 2007 and 8. But as you can see, in 2009, it started to come back. And what you've got now in 2015 is traffic volumes approaching what they were in 2006, and that's non-sustainable. So there is dawning realization that traffic must be managed, and congestion must be managed in such a way as to start trying to change the volume statistics and to change the way the volume is used across the day and night. Any questions before I move on? Yes, there is. He's held up a finger.
Yes, so we have a question. It's asking, is that result similar across countries?
Oh, that's a good question. Yes, it is. Now, there are certain areas where it's not the same. But let's, in parts of Africa, it certainly isn't, isn't like this. But in most areas of the world that I visit, and most areas of the world that I'm working with, yes, it's very similar. We're certainly seeing traffic increasing in the Middle East. We're certainly seeing traffic increasing in Vietnam. In fact, if you read your press at the moment, Indonesia and Vietnam are building thousands of kilometers of freeways right now, just to try and put better infrastructure in place for the amount of volume that's on the roads at this point. Yeah, I believe it is pretty much static across the, Asia, frankly, is and obviously this presentation is based around Asia and Asia time, is suffering this more so than anybody else probably, because their volumes have increased tremendously over the last 20 or 30 years as opposed to what we're experiencing in North America. Any other questions?
None at this time.
Okay, so let's understand some of the market drivers and some of the reasons why we've got to get congestion down. The first one is that I'm going to talk about MAP 21. That's moving ahead for progress in the 21st century. And basically it's a federal requirement, and it's not rolled out anywhere else in the world, but other countries are certainly looking at it because it does actually give a reason for getting quantified improvement. But the idea behind it is the federal government gives each of the states so much money to improve roads. Okay, what they've finally said is, you know what, despite all this money we're giving away, we can't really see much improvement. So therefore, moving ahead for progress in the 21st century states quite categorically, if you do not see quantifiable improvement, you will not get any more federal funding. And that's huge. And they've even gone so far to actually try and identify how you can prove it. And I'm going to go through the first three, which is travel time reliability. That's basically saying, I want to go from A to B. How long does it take me in 1999? How long does it take me in 2014? Is it better or worse? If it's worse, then it's not good. I'll put it that way. Average speed by time of day, average volume by time of day. Let's look at that. Because if volumes are always increasing, which we know they are, and volumes relate to speed, and speed relates to travel time reliability, you're sunk before you start, unless you can get those volumes down somehow. And to get those volumes down, what they're looking at doing is looking at anything they can actually start charging people for, anything they can start doing congestion mitigation strategies for. So you've got congestion charging, such as London, Stockholm, and just now New York's certainly looking at it again. They looked at it about 10 years ago, and now they're reopening that book. San Francisco is looking at it. Basically, any metropolitan area which isn't looking at this, well, actually, I'll put it another way. Most metropolitan areas are now looking at some form of congestion charging. Now, congestion charging follows many routes, as like anything else does. That can be high-frequency vehicle lanes. Instead of 2 people, it's 3 people. Hot lanes, that's high-frequency tolling, which basically means that basically you're getting charged not only for using the road, but also getting charged more depending on how much volume is on the road. And that's huge as well, because what that essentially does is suggest to people that if they can change their traveling habits and not go in at rush hour, actually you don't have to pay as much, or anything at all in some cases. Freight user charging is also another area. Let's charge freight because they tear up the roads more, and therefore, if we can actually start charging them, we can get something. And probably the biggest thing in all this is open road tolling. But to be blunt, there are more cameras being used on the roads than ever before. Open road tolling has been probably the largest usage of that. I know of one state here who's looking at putting thousands of cameras on the roads to actually start really identifying, as a sensor effectively, start identifying what's happening on those roads. Sorry, there was a question.
Sure. Kind of have a few here. So I'll start with the first one. How can you be so sure about MAP 21 when it has yet to be ratified?
That's a good question. I have actually sat on some of the MAP 21 focus groups, and it will be ratified. There has to be some changes. At this moment in time, there's more funding being spent on general road improvements without any real indication that whatever's being built or a capital project that's being proposed will actually make a real difference. You know, we're in a situation that capital projects simply are now seen to not be working, and therefore there has to be another approach.
All right, so I'll move on to the second. What is freight user charging?
Oh, that's a good question, actually. That's identifying every truck on a road has to pay for every kilometer they drive or every mile they drive. And the idea behind it is that, again, you're using normal tolling mechanisms, so you can use a camera or you can use a toll tag, but those trucks are, you know, and it's an automatic payment process. It's not like you have to stop and pay, you know, with cash. But the idea behind it is, again, to get freight off the roads at busy times. As an example, Spain is a really good, or Madrid anyway, is a really good example of this. Freight is not allowed anywhere close to Madrid city centre during peak hours. Now that's not freight user charging, but it is freight prevention during peak hours.
Okay, and the last question I have here that came up is where does open road tolling fit into this approach?
Well, actually, I think it's probably the biggest thing. It's certainly the biggest thing that's being worked on at the moment. Basically, there are more and more roads, and I'm talking about thousands of kilometers of miles of roads being put to tolling mechanisms. And the whole idea of open road tolling is that instead of having a stop-start where you have to pay money in cash, it's a completely electronic process where you have an electronic wallet that's automatically deducted by a certain amount every time you use that piece of road. But the beauty of open road tolling is there's no slowdown. You don't have to go down to 5 miles an hour or 15 kilometers an hour. It really is a case of 65 miles an hour, and a lot faster for that matter. I think at the moment they're working up to about 125 miles an hour speeds, but not that many people, not that many countries allow that. In fact, I can only think of Germany, in fact. So, and I was there just recently. It was fun. Anyway, next. So the drivers for change. I've gone through some of these. Economic downturn. There's a dawning realization that additional lanes just don't help. What happens is that after about 3 lanes, they become more and more inefficient. I write a newsletter every week, and actually the main part of this next newsletter will be about driver habits and how to actually make lanes more efficient by changing driver habits. But the fact of the matter is it really comes down to the human being, which they're not pulling over to the right or left, whichever side of the road you drive on, and therefore they're effectively clogging that road. You effectively have this moving body which is actually preventing anybody faster going past them. I think some of the other things that are really going to make a real difference is that ANPR, automatic number plate recognition software, is going to come down in price. We've already seen that. At the moment, you can have costs anything from, I think the lowest I've seen is about $900 per license, anything up to $1,500 per license. But there are more and more companies doing very good systems, and therefore there's going to be more competition. But the congestion mitigation strategies are really going to be the things that we know and love, the integrated corridor management, really trying to manage that as a collective, and the smart transportation, smart city, which we've all seen. Sorry.
Then I think this question is probably the most obvious asked. Could you elaborate on why you believe more lanes of freeways become less efficient?
Oh yeah, I've pretty much hit that one, but it really comes down to driver behavior. And I'm as bad as everybody else. Please don't think I'm a saint here. I'll sit in the third lane because there's two more to the left of me. You know, and that's exactly why it's a bit inefficient. You know, because we get lazy. Instead of pulling over and actually allowing that road to be really clear, you know, there's nothing in front of me. There's nothing really behind me. There's only 15 cars waiting. You know, I can sit here. They can go past me, and that's why. You know, but it's really inefficient. So the road to improvement. Not sure there's a pun there. It wasn't meant to be a pun until this moment, but anyway, moving forward. Looking at where we are at the moment, we've got all this data coming in from all these different sensors, and what we're effectively getting, you know, we're looking at the real time, we're looking at the long-term historic, we're looking at the short-term historic, and we get a pseudo prediction, which is about 50% accurate at best. But it's because we've got all this data, and we really haven't got any way of managing this data in a big data philosophy kind of point. And as you can see, as we move forward on this, we can actually have a much better approach to this. And this is using the approach we currently have today, and the next slide will actually show you what I'm proposing as we move forward. But we've got the raw data that's coming from ITS infrastructure. We've got the processes. That's really coming from the cleanse, validate, from the extract, transform, and load. And then we've got the systems, the advanced traffic management system, which actually all this data gets pumped into. Unfortunately, it then sort of the chain breaks a little bit because everything else becomes manually input. So all the information elements are all the additional elements that are being put in by the human, where there's accidents, where there's construction, you know, all of that, where there's a dead animal on the road, that's all manually entered, and that's really what, you know, brings a grinding halt to some of this. But from that, we get the intelligence bit, like the automated updated DMS signs, but they're not automated at the moment. They're really very much manually controlled. Sorry, quick question.
Yes, we actually have two questions here. So the first is there a privacy issue with ANPR?
Yes, there is. Well, there is and isn't. It depends on which country you sit in. If you're in Germany, there's a huge issue. In fact, ANPR is absolutely not allowed in Germany, except for government offices, and even then it's frankly frowned upon. And I know this very specifically because I was just trying to get testing undertaken in Germany. So there's a real issue there. In other countries, it depends on how the data is being used and how the data is managed. Let me be clear here. You can change the number plate to using a variety of different algorithms, but to create hash codes. And those hash codes can then be used because they can't identify the vehicle. And even those are allowed in Germany. So you can get around it. And basically, in Germany, though, particularly, you have to look from behind. You can't look in the front because if you looked at the front, you could essentially use facial recognition software to identify the person, in theory. So it has to all be from behind. There are always going to be some kind of privacy issues with ANPR. The fact of the matter is those privacy issues are going away more and more because people are starting to, or governments are starting to realize that actually the data is there anyway. The data is there through, as an example, Bluetooth. The data is there through toll tag readers. The data is there through cellular communication. You know, in fact, I will be very candid with everybody. You know, I know for a fact the FBI managed to track down the New York bomber through their cell phone. So, you know, we can all be tracked should we want to be. So I think they're going to go away. But yes, there are at the moment, but they will go away. And that's only in certain geographies. In other geographies, such as North America, that really isn't an issue. In most of Europe, that's not an issue either. So for instance, as an example, one of the most prevalent forms of cameras being used in traffic right now are the dashboard cams to prevent accidents. Now, they, at the moment, are banned in Germany, but not banned in the rest of Europe because they're seen as a valuable aid. But you can run those through ANPR software and get an indication of every vehicle on the road that you're passing or they're passing you. Sorry, you had another one.
Yep, and there's one more question here, and it's kind of maybe tripling a little off the first one here. Can ANPR be used for generating traffic data such as speed and travel time?
Yes, a good question actually. Yeah, it can. Yes, it can. I'm thinking about how to formulate the answer a little bit. The first one is speed. There are ways of identifying speed very easily now with a single camera solution without triggering. Okay, that can either be through the camera itself, or can be through using mechanisms on the road, such as a white line as an example, multiple white lines. You can also use cameras in stereo to do the same thing, but it becomes expensive, and I'm not recommending that right now. What I am recommending, however, is that a single camera can be used for speed over distance, and distance can be very short, i.e. a few tens of yards, by using just the camera itself. Speed over distance can be done by, and it is being undertaken, particularly in tolling environments, for open road tolling, whereby you can identify when a vehicle's gone past one gantry, and then 15 miles down the road you can identify when it's gone past another one. Given that you've just gone 15 miles, it's taking you so long, you can do speed over distance quite easily. Any other questions on that?
No.
Okay. Moving forward on this one again, and this is a sort of a multi-level slide. We've gone through the raw data, we've gone through the fact that data is cleansed, we've gone through the fact that it then goes into the advanced traffic management system. It then gets this almost manual stuff being entered, and then some intelligence gets out, gets pushed back to the operator for them to do a command, whether that's DMS sign or variable speed control or traffic light phasing. Now my argument here is, if we inject a camera into this, what we can effectively do here, we can get rid of the raw data because that's coming directly from the camera. So it's not got this plethora of different systems, it's just one. We get rid of a lot of the process because that's being done at the front end from the camera. That can go fed directly into the ATMS system. The information can actually be the safety systems we spoke about, such as accident detection, debris on road, wrong way running, pedestrians on road, etc. And from that, we can automatically give the intelligence either back to the operator or indeed get the system itself to do the work for us. Now that's going to take some time, but certainly within an integrated corridor management or a smart city environment, that won't take long at all. I mean, that's a natural progression, either to do it as a single step or a two-step solution. But using clever software, that single camera can give you speed, occupancy, volume classification, wrong way running, and a host of other things, including overhigh vehicles, which at the moment there is no single system out there which can do that. Hazardous materials, etc. And again, that could be really beneficial. Just identifying what vehicles are going down the road, what materials they're carrying, could be absolutely imperative when it comes to, as an example, I can't think of the word now, but evacuation type planning environment. So in conclusion, do I really believe that valuable data can be delivered? I think as we've gone through this, it's pretty obvious I do. But actually I'm going to go one step further. I actually believe it will become the de facto standard for all ITS data collection. I think it's the only thing that makes sense. I'm not saying that, and anybody that knows me will know, I'm not saying that just because I'm working within visual, machine vision organization. I'm saying that because it's actually something I passionately believe in. That comes down to the question we asked. It will only work in countries which enable ANPR. If you don't enable ANPR, it won't be available. It won't be able to do everything I've said here. Still be able to do things like the debris and road and wrong way running, etc. But it won't be able to do speed over distance or any of the other cool stuff we've been talking about. But with the integration of an ANPR camera, I think you'll get better data, a better quality of data, and you'll actually get the microscopic model we've all been talking about. It will also give you the predictive environment that we need to really manage the road. But there's three other things here. It will give us the ability to manage the road, it will give us the ability to manage congestion, and more importantly, it will give us the ability to understand where capital road building projects are necessary, where there's a bottleneck which cannot be overcome by just better planning or better utilizing the data. So anyway, that's all I've got time for today. I'm hoping there's a few questions, but keep the questions coming. We've got as long as you've got. Francis doesn't want to get home into his bed anytime soon, so that's fine. So anyway, any questions, Francis?
So we do have one question, and it's, does the occupancy work in Asian cities?
Oh, that's a really leading question, because however I answer that is going to be no, it's going to be wrong. It depends on which Asian city. It depends on the traffic makeup of the Asian city. So, for instance, when you've got high propensity of motorcycles, actually it's really quite a clever question, because when you've got high occupancy of motorcycles, it probably won't work as efficiently. That said, the software within ANPR is becoming so good now it can identify 2 bicycles versus 2 motorbikes or 2 scooters. So will it work? Not right now. Will it work in 18 months? I'll put $50 on it will, if somebody wants to take me up on it. So.
And the asker actually clarified Mumbai was.
Mumbai.
Mumbai.
Oh, that's even okay. Well, there's even a bigger, greater issue in Mumbai, and that's the fact that the license plates aren't standardized. So what you're getting is quite a lot of license plates which are written manually. Quite a lot of number plates which are partially covered by, I don't really know what to call them, the little dangly bits, glitter and stuff, which are put onto vehicles, to really make them look special. Now, that said, yes, it will work, because the idea behind it is that what we're looking for is patterns. And ANPR software and OCR software is getting much better at looking at patterns. So even if it can't identify the fact that a license plate has been handwritten, or indeed what it is, it can identify the fact that the license plate is the same in place A to place B. Now, is that software as 100% accurate as the OCR is? Not yet, but it's certainly good enough to give speed over distance. Definitely.
Okay. We have another question. How does hyperlocal weather play a role in ITS?
How does
hyperlocal weather?
Well, obviously, weather plays a huge impact on any ITS solution. When I was working on real-time, and I started doing a PhD on mathematical simulation of real-time systems, and what we were able to identify there was there were about 7 different elements that played a part in really identifying a predictive model. And there were things like short-term historic data, long-term historic data, real-time data, maintenance data, maintenance being construction data. But one of those major elements was also weather data. It plays a huge impact. That said, and one of the things I really want to stress here, some time ago, I'm looking back to my childhood, which is a hell of a long while ago, but back to my childhood, which was, you could look at the television every evening and tell you what the weather forecast was being. I did some analysis, and that basically said that 80% of the time it was wrong. Now, this is in England. 80% of the time it rains. How can you be wrong? But anyway, now not only is it right, they can tell you almost to the 10-minute segment of when something's going to happen. So with that kind of modeling, that obviously it plays a huge impact on your ITS, but it can be managed within that microscopic model. We know when there's going to be icing on the roads. We know when there's going to be rainstorms. We know that it's going to be flooding in certain areas, because again, using the big data philosophies and visualization data, and Esri is doing a fantastic job on some of this stuff. But as an example, one of the models I saw recently was floodplains and the impact of floodplains on ITS. And again, using those big data models, what we could easily do is identify, as an example in monsoon seasons, which roads are going to be flooded, what the impact of those roads are going to be, where the traffic is going to go, and how to actually mitigate some of the traffic congestion you would otherwise have. So yeah, it plays a huge impact, but I think ultimately it will be managed.
Okay, we have another question. What are the key things stopping the use of ANPR more widely, being used more widely now?
Well, I think the first one is privacy. There's clearly a privacy lobby. I think I'm going to speak candidly, but I think that's got more to do with a lack of understanding of what ANPR is and what it's going to be used for rather than anything else. The second one is the licensing cost of ANPR software, which at the moment makes for many applications it cost prohibitive, although I think that's going to change. And the third thing is I think there has to be some infrastructure to mount cameras, and there also has to be back office systems to collect the data that's coming back from it. Having said that, I think with the right approach, the amount of data coming from a camera can actually be limited to a very small number of K.
We do have another question. How is accuracy of vehicle occupancy detection influenced by the type of vehicle?
That's a good question. I'm really having to think about that. Well, if you accept that part of the, as I said right at the beginning, part of the, it was speed, occupancy, and volume, but now it's becoming speed, occupancy, volume, and classification. Classification is actually a key. It's absolutely essential. If we know the classification of the vehicle, then it's very important to also know the occupancy, and the occupancy will not be fooled. If we don't know the classification of the vehicle, then clearly there could be an issue there. With clever software, and I keep using the word clever because I do feel that actually it's going to be more important, the software element is going to be more important than the hardware element, but with the use of clever software, the occupancy and the categorization would be very, very accurate, more accurate than any other technology so far available. I'll give you a more full answer on that one when I respond to those in writing.
That's all the questions right now. I think if it's okay with you, Jorgen, maybe just give a little bit of time just to see if anyone is still trying to formulate any questions they might want to ask.
Certainly, and again, my email address is on this slide. My phone number is on the slide. If there's anything you want to ask me, then please feel free to do so. You can send me an email. All questions, I will only say that all questions, unless they're specifically asked to remain private, will be written up and distributed as well and made available, I think, on the website as well, right?
Yeah.
So the presentation in PDF form and some of the animation will have to come out of that, obviously, will also be made available. But one thing I will say is I hope it's been useful. The idea is to do these pretty much monthly, or every 6 weeks or so. So if there's anything you want to hear about, is there anything you want to get more information on, again, put the ideas forward. I think the next two are scheduled already, or scheduled, depending where you are. But by the same token, if you want to, as an example, hear more about a particular element of ITS, I'd be more than happy to try and bring that together for you.
We don't have any new questions at this juncture. So, Jorgen, I turn it to you. Do you want to
thank you.
Things?
Yeah, thank you very much. I really appreciate everybody's time. I hope it's been of use. If there's anything you think we should improve, then please feel free to put those suggestions forward. But otherwise, I very much hope to see you again or have your attendance at the next webinars. Thank you so much for your time.
Thank you, everyone, for joining us. We look forward to you guys joining us at our next webinar next month.
Thank you. Bye-bye.